Algebra 2 students, remember all the things we've learned about solving quadratic equations, and today we're going to start looking at how do you graph quadratic functions. So, y equals ax squared plus bx plus c is a quadratic function. I like f of x equals ax squared plus bx plus c. But they mean the same thing. This is in function notation. Remember, f of x is just y. Y is some function of x. We're going to start with a really simple graph of f of x equals x squared. And like all graphs, if you don't know how they look, you just start by plotting points. So let's take y equals f of x, which equals x squared, and let's just make a chart of x values and figure out y values. And something I know that you need to know is that quadratics are part of a bigger family called polynomials, and you can plug in whatever you want for x. There are no domain restrictions. So I'm going to start with -3, -2, -1, 0, 1, 2, and 3. And then it's pretty easy function. All that this function does is takes the x value and squares it. So -3 squared is 9, -2 squared is 4, -1 squared is 1, 0 squared is 0, 1 squared is 1, 2 squared is 4, and 3 squared is 9, and hopefully you're starting to see some symmetry. If I were to graph those points, I'll use a nice red color here, make it easier to see. 0, 0, 1, 1, 2, 4, 3, 9, -3, +9, -2, +4, -1, +1. You start to see this symmetry here, and the shape is a curved one, and I'm doing the best I can with this. There we go. Much better on a whiteboard, but I'm getting there on my tablet here thing. So here we go. Here's our shape. This is what we see. Over 4 up 16, over 5 up 25, over 10 up 100. As you move over in x, you move up whatever that value squared is from this point here. Labeling some of these things, we call this point here the vertex. It is the minimum or maximum of a quadratic function. Sometimes quadratic functions look like this but flip down. There's also this vertical line here that goes through the vertex, and we call that vertical line that goes through the vertex the axis of symmetry. All quadratics have a vertical symmetry, meaning there's a vertical line that cuts them in half at which it's mirrored. Notice this point here is mirrored over that axis of symmetry. The same with this point here and the same with this point here. You're going to want to know this basic function x squared and how it works. Over 1, up 1, over 2, up 4, over 3, up 9, over 4, up 16, back 4, up 16, back 5, up 25. And when I say those things, I'm talking about moving from this point here. Over 1, up 1, back 1, up 1, back 2, up 4, back 3, up 9, back 10, up 100. You're just squaring. Back 7, up 49, back 8, up 64. Just squaring those values and see how quickly this thing rises. Now if I was to graph the line y equals x, they would hit here and then there. And just to show you that y equals x is actually bigger than x squared between 0 and 1, but that's something you should know. Kind of obvious. We're going to talk about this function y equals f of x equals x squared, and then we're going to talk about how can you take this function and transform it and move it around, pretty easily. So let's take a look at this idea here. For any function y equals f of x, remember we talked about earlier in the year y equals a times f of b times x minus h plus k. And remember at the end of last semester, we talked about how h and k move things left and right, and k moves things up and down. And a and b, depending on where they are in the function, either vertically stretch or vertically shrink, or horizontally stretch or horizontally shrink the graph. X squared is a unique function where if I take 2x and square it, that's the same as taking 4x squared. So a b value of 2 is the same as an a value of 4. And so I'm not going to worry about this parameter for quadratics, because for the most part with quadratics we can deal with that same thing as an a value. So reviewing hopefully a little, let's go back to our graph. Let's graph the function y equals x squared. So that's the function we had here earlier. And then I'm going to graph the function, a couple different transformations of this function in different colors. So I'm going to graph y equals x minus 5 quantity squared. So notice that the minus 5, it's inside parentheses, it's being squared, so that's an h parameter. So that would move this over here to 5, and then from this point I would go over 1, up 1, over 2, up 4, back 1, up 1, back 2, up 4. Notice I'm moving from that vertex, and I get this graph here. And I encourage you to plot points to check to see that my graph's the same. Plug in 7. What's 7 minus 5? 2. What's 2 squared? 4. Plug in 6. 6 minus 5 is 1. 1 squared is 1. Plug in 3. 3 minus 5 is negative 2. Negative 2 squared is 4. So notice it's this 5, when x equals 5, that's acting like a 0 inside the parenthesis. That's why we've moved out here. Different color, I'm going to graph the function y equals x minus 3 quantity squared plus 2. Alright, so using the idea of transformation, the minus, or sorry, I'm going to make it plus 3. The plus 3 would move me back here 3, and the plus 2 would move me up here 2. From this point, over 1, up 1, over 2, up 4, back 1, up 1, back 2, up 4, 1, 2, 3, 4. And I have this exact same shape that I've graphed now 3 times, but I've moved it to this point, negative 3, comma 2 is the vertex. Back 3, up 2. That plus 3 moving it back, the plus 2 moving it up. Plug in a point and check. Plug in the value of x equals negative 5. What's negative 5 plus 3? Minus 2. What's minus 2 squared? 4. What's 4 plus 2? 6. So there's the plus 2 and there's the 4 to give you that value of negative 5 comma 6. Last function I'll graph here on this axis in black. If I said y equals negative 2x squared. So I'm not moving from 0, 0 at all, but this negative 2 is going to take all the y values, stretch them by a factor of 2, and flip them over the x-axis. So over 1 down 2, over 4 down 8, back 1 down 2, back 2 down 8. Now why am I going down 8? Over 2, square that, that's 4. Take 4, multiply by negative 2, and you get negative 8. And you get this vertical stretch. This is a different shape altogether. Good? So there's a couple parameters here that we got to worry about. We got to worry about what this a value is in front of the function. We've got to worry about what this h value is inside the function, and we've got to worry about what this k value is outside the function being added or subtracted. So if I give you something with all of those parameters, y equals, we're going to make this really hard, y equals 2/3 x plus 7 quantity squared minus 4. The first thing to do is identify what all your parameters are. A is 2/3. h is equal to -7, and k is equal to -4. Once you've identified your h and k, go to that point, -7, -4, and what I like to do is I go to that point, and I'm going to treat this like my new 0, 0. Treating this hk like 0, 0 means all I have to graph from that point is y equals ax squared. I've taken care of what the h and k will do in terms of transformation if I move to this point and I graph from there. So now I know what 2/3 is going to do. It's going to vertically shrink the graph. So if the absolute value of a is less than 1 but bigger than 0, you're going to get a vertical shrink. And if the absolute value of a is bigger than 1, you're going to get a vertical stretch. So this graph is going to be vertically shrunk, and because a is positive, I know it's going to be opening up. So it's a vertical shrink and it opens up. Now I can plug in 1, and 1 squared is 1, and then I would go up 1 times 2/3, which is 2/3. Or I go back 1 and up 2/3, but those aren't nice values. So I'm going to pick a nice value like 3. And the reason I'm going to pick a value like 3 is because if I take 3 and square it and I multiply by 2/3, I'm going to get a nice value. If this was 1/4, I would have picked 2 because 2 squared is 4. If this was 1/5, I would pick 5 and so on. I hope that makes sense. If this was 1/4, I would still pick 2, or sorry, 1/2, I would still pick 2. You know, just some things to think about because I want to get a nice number. So I'm going to go over 3. 1, 2, and 3. If I plug in this value of x, -4, I should get a 3 inside the parenthesis. Check my math. -4 plus 7 is +3. +3 squared is 9. But instead of going over 3 and up 9, I'm going to go up 2/3 times 9. So what is 2/3 times 9? I hope you said 6. So I'm going to go over 3 and up. 1, 2, 3, 4, 5, 6. Now I'm going to use symmetry to get this other point. Back 1, 2, 3, and up 6. So I've got this nice symmetry, remember, so I don't have to do too much work. And now I can plot this quadratic function that looks like this. Good? If I were to superimpose the graph y equals x squared from that same vertex, over 1, up 1, over 2, up 1, 2, 3, 4, over 3, up 9, I hope you can see that it is vertically stretch. I should use some parentheses here. Vertically stretched compared to the graph in the blue, right? So this is the original function. This is when a equals 1. So do you see why we call this blue graph vertically shrunk? It's like it's been smushed down just a little bit. Not much, but a little. Good? And that difference will be more and more pronounced as you take further values of x away from the vertex. So if I had to pick another point, I'd pick 6. I would go over 6. So 1, 2, 3. 3 more from there. 6 squared is 36. 36 times 2/3, right? So 1/3 of 36 is 12. 12 times 2 is 24. You would go up 24. Again, if there was no stretch at all, like in the A graph, you would go over 6 and up 36. But because of this vertical shrink, I'm only going up 24. Now, it's still pretty big, but it's not as big as 36. Hope that made sense. I'm going to give you lots of practice on graphing quadratics. Just so you know, every quadratic you're going to graph right now is going to be of the following form. Y equals x squared, and then the transformation, y equals a times x minus h, quantity squared plus k. We call this vertex form. The reason it's called vertex form is because the vertex is always the point h comma k. And then that means the axis of symmetry is always the line x equals h. And the a value tells you if it's up or down, or if there's a vertical stretch or shrink. Good? All right, lots of practice graphing tomorrow. Have a good weekend. Peace.